Hello everyone! In this video we will begin to examine topic 5.4, the magnetic effects of electric currents, and in particular we will begin to understand magnetic fields. Okay, so in topic 5.4 we're going to investigate magnetism, okay? And it's the entirety of what we'll do with magnetism in the core material. HL, you'll do a little more. I'm going to start not with sort of the primary idea that you'll be responsible for in this unit, but I'm going to start actually with what our ordinary everyday experience of magnets and magnetism is. And so we're going to consider simple bar magnets. And I'm going to appeal a little bit to your childhood, and hopefully you've seen some of this before, but let's describe sort of how a simple bar magnet works in the ways that we're familiar with. So bar magnets, as you might know, have two poles. So not charges or positive negative charge, they have what are called poles, the north and south pole. But the north and south poles interact a lot like charges do, in that unlike poles attract, and then like poles repel if the magnets come nearby. So there's this extra force. Notice it is not, at least not obviously, related to the electric force. It is not about the accumulation of static charges. It is not gravitational, so this is a new kind of interaction that is happening here that is not explicable using the physics we've already discussed. It does obey Newton's laws, but then again, all forces do. So this is a new sort of origin of a force that we're going to want to explain and characterize. The final thing to note about magnets, which we'll be explaining sort of near the end of this unit, is that they are attracted to some but not all metals. Okay, so magnets do end up attracted to some but not all metals, known as ferromagnetic materials. And in our ordinary everyday experience, this is actually the most common way in which people experience magnetism. There are a couple of other ways, but usually if you mention magnetism, this is what people have in mind. So the question is, why is this happening? How is this happening? What is magnetism? And as it turns out, the permanent magnets in these examples are actually really difficult to fully explain. They require a lot of physics and a lot of understanding of what is going on at a microscopic level. But we'll get there, and we can start by appealing to an idea that, as it turns out, is going to be extremely useful in explaining their action and other magnetic phenomena that we are less familiar with, and that is the idea of a magnetic field. So I want you to consider the effect of a large bar magnet on a tiny bar magnet, okay? Free to spin but held in place. A tiny bar magnet that is free to spin but held in place is known as a compass. And you're probably familiar with compasses from just living in the world. They're the things that point north, which is a phenomenon we'll explain as well. The tiny bar magnet, free to spin but held in place, is also known as a magnetic dipole because it has two poles, a north and a south. So what happens? Well, if you put your large bar magnet down on a piece of paper and you take your compass and you put the compass all the way around the bar magnet, you'll discover that the direction of the compass changes. So normally compasses point north, but if you put it near a bar magnet, you will discover very quickly that the bar magnet is going to significantly affect the direction of that compass, as that compass is also a little bar magnet. And you can represent the compass direction at any point with an arrow, pointing that arrow representing the bar magnet points from south to north within the bar magnet. Okay, and so if you put it all around your magnet, you will discover that the compass lines up like this, as shown here. And Fundamentally, if you look at sort of the areas near the North Pole and the South Pole, that makes sense, right? So if you have a tiny little bar magnet, then the north side of that bar magnet will be repelled from the north end of this major bar magnet here. So the north side of the compass is repelled from the north side of the bar magnet. The south side is attracted, and so it lines up pointing away. Notice the opposite is true for the South Pole. What may be less obvious is the direction that the magnet will line up in this region and this region. And you'll notice that this pattern here forms a very clear and reminiscent pattern. And we call sort of the structure of these arrows, the structure of what this turning force would be, we call that the magnetic field, symbolized with B. So just like electric field and gravitational field, you have a source, okay, that's our bar magnet, and that source is producing an invisible field all around it, and you can see the effects on that field by putting the little compass sort of at different points, and it will rotate to line up with the field. Okay, so we say that the bar magnet produces this field in the space around it and then acts a force of a particular sort on the compass, turning it in the appropriate direction. As it turns out, if you use tiny little iron filings or little bits of iron and you sort of place that over the magnet, so you place the iron filings over the magnet, then you will get a pattern that looks exactly like those field designs here. So you'll get a pattern this is actually a different physical setup, but you'll get a pattern that looks something like this that can help you visualize the magnetic field and the magnetic field lines, although they do not have the arrow direction. Okay, that arrow direction comes from the compass exclusively. So our preliminary definition of the magnetic field, given this capital V vector, is that it is a region of space in which a magnetic dipole experiences a torque or turning force. Note that we haven't covered torques in this class, but if you've seen them before, if you've heard the term, this is basically a turning force. It's a way of understanding how forces act on objects that cause them to rotate rather than to translate, to move in one direction or another. And that's as much of an understanding as you need for this class. There is more, but that will suffice for us for now. Notice that the direction of that magnetic field is determined by the direction a small test dipole would turn, aka your compass. The strength of the magnetic field is related to the strength of the torque, so how much torque would it apply? And our magnetic field is a vector field. It does have a direction and a magnitude at every single point in space. And that vector field can be pretty straightforwardly visualized with either the compass sort of moving around and drawing those arrows or with iron filings.